you, Roberta, for the introduction. So, hi. I'm a PhD student at the CNRM Research Institute at Météo France. And I work at the ville team that, if you translate to English, means city. So I'm going to change a little bit of the context for my presentation. My PhD, the main topic is the statistical downscaling for urban temperature at hectometric scale, so very fine scale, and we focus on urban environment. So a little bit of context. So why this research is important. Today, more than 50% of the world's population lives in cities, and it's also big, important places where socio-economic activity is based today. And also, we need to care for the people and their comfort. So having an urban weather forecasting of big quality for urban environment is very important. And we also need to better understand and characterize urban phenomena, such as the urban heat island. So today's weather forecasting for any type of environment is done either by global models, which can cover large spatial domains, but are too coarse to reproduce fine-scale phenomena, which is going to be interesting for urban weather forecasting, or either by limited area models that are a little bit more numerically expensive, but could give us this information, fine-scale information. So then there was statistical downscaling and machine learning, which are, so statistical downscaling models try to link large-scale data to local variables over a given domain in order to improve the resolution of any type of data. Could be spatial resolution, that's going to be the work that I'm presented, but also could be temporal resolution, as someone mentioned yesterday. So we're trying to learn the statistical relationships between the low resolution and the fine scale. And it's been really already used in the climate community and the weather forecasting community. And machine learning techniques range from simple regressions to quantitative mapping and more deep learning techniques. But what is important in the urban context is that a robust methodology is still to be built. So this is a plot from a paper published by Lewis Blunt at the Met Office, and they tried to downscale urban temperature over the city of London during heat waves. So you have different machine learning models plotted in the plane lines compared to the observation sites deployed by the Met Office in dotted line. And they tried to evaluate which machine learning models performed best. But it stayed like a point-wise downscaling. So the goal of my PhD is to do this statistical downscaling using large-scale resolution simulations to provide the temperature field at 2 meters from the surface at a fine scale over the city of Paris to start with. And I'm going to do that thanks to neural networks. So maybe I will take a little bit of time to present my domain of study. So this is the city of Paris, capital of France. So as I said during my introduction, one of the main objectives, I don't know, one of the main phenomena that we observe in cities and that is very interesting and important to characterize is the urban heat island. This phenomena occurs when there's a lower temperature at the rural environment compared to the temperature that we could find at the city center. So this would be the intramuros Paris, the city of Paris. And so you can see that we have much greater temperature over the densely urbanized area of the domain, and also like the surroundings and more the outskirts of the city that is also urbanized compared to the rural and countryside. So these are the Boulogne forest and Vincennes forest. These are two very large forests in the west and east of Paris. And during the occurrence of urban heat island, we will register lower temperatures around these areas because of the cooling effects of green zones. So we'll be looking at them during the presentation also. So little outline of my presentation. First, I'm going to introduce which hectometric simulations I'll be using for my work. Then I will set a perfect model environment and show you some results within this setup. Then I will show you the downscaling of AROM simulations, which is the operational model, weather forecasting model at Meteo France. And finally, we'll discuss and I will show you some future work. So, as I said, I'm trying to downscale large-scale simulations to hectometric scale simulations. So, because I use supervised learning, I need the ground truth, so some fine-scale data to compare to train my model. So I'll be using MESO-NH. This is a research model that we use at CNRM, which is a very fine-scale model that we could set up in various domains. This is a little bit of information about the configuration of the MESO-NH. I'm not personally an expert on MESO-NH, so if you have any questions about this, I will refer you to my supervisors. But what I could tell you is that for the land cover database model, we are using Surfx v9. And within Surfx, there are different types of environment that I model. Notably, we have the TEP model that is town energy balance, which will model the interactions between the urban surface and the atmosphere. And also within TEP, we have the BEM model, which is building energy model, which also, well, better represents urban environments. So for the MESO-NH configuration, we have two different nested domains which interact within each other during the simulation. The blue domain would be like an initialization domain, which is initialized also by AROM, 1.3 kilometers. And then we'll have the red domain, which will be my domain of interest, which is a 300-meter resolution domain. That will be my targeted resolution for my downscaling. Because MESO-NH is such a computationally expensive model, I didn't have much data to train my model with, so I did kind of statistical study of the climatology of the Paris region in order to select a year of non-consecutive days in this period in order to better represent the climatology of Paris and limit my number of simulations with MESO-NH. So we could talk about this a little bit later if you want to. So I have a year of MESO-NH simulations. I have 3 hourly outputs from 9 to 33 lead time. And I divide this year into my training set and my validation set, which gives me a total of around 3,000 fields for training and 300 for validation. And then we did another round of simulations to simulate 3 independent months that I'll be using for my test sets. that have been selected following the same strategy that these dates. So, you know about my small-scale simulations. What about my large-scale simulations? So first, I place myself on a perfect model setup, meaning that I'm going only to care about the super resolution task. In practice, what that means is that I'll be degrading manually my 300-meter resolution Meson-H fields to 4 different resolutions, 1.2, 2.4, 5K, and 10K. So the model can just focus on recovering the small-scale details and not much about the physics of the domain. It was very practical, indeed, because the domains are identical. This is not the case if we try to go from AROM to Meson-H data because of the projections and whatever. And also, much of the urban signal is already included in my degraded Meson-H fields, such as the urban heat island. So it was like a first step in order to achieve the downscaling, to simplify the problem. And now I'm going to present some results for the 5K to 300 meter downscaling task. Oh yeah, so my architecture. So I'm using a simple UNet. It's a classic CNN neural net, CNN architecture that's been used already by some people in the community of climate science. This is maybe why I use such simple architectures, is because there were people around me that knew about it and were familiar with it. So for my input variables, I have, of course, my large-scale temperature fields, 2-meter temperature fields, derived from the degraded Meson-H. Then I have a lead time predictor in order to help the model to identify when to create these urban heat island effects. And this is done classically in the classic model of cosinus and sinus form of the lead time of my model. And then for the target, I'm targeting the Meson-H original simulation at 300-meter resolution. Some technical details. Maybe note that my loss function was a simple MSE, and we'll be talking about that later. So some results. In the figure in the top, you can see the input, so degraded Meson-H of my model, at 3 different lead times, so 6 p.m., 9 p.m., and midnight for the 13th of May 2019. I selected this date for my test case because we can observe a very clear urban heat island, and there were clear sky conditions, so it was very easy to analyze from a meteorological standpoint. In the middle, we have the outputs for my downscaling model, and in the bottom, the targeted fields. So, as David explained this morning, as expected, my output fields are very smooth. Some good points though. So we have good intensity over all time of environments and good reproduction, somehow reproduction of spatial structures, namely the urban heat island, even if it was already contained in the original fields, and somehow of good cooling effects over the 2 urban forests that I mentioned earlier. But of course, we observed these smoothing effects. So my question was, how could we improve that? And I followed different leads, so I had several ideas on how to improve this, and maybe we could talk about everything later, but I'm going to present the 2 main modifications that I did to my network. The first one was, of course, the custom the loss function that I used for my training. So a Sobol operator is a very classical image processing filter that we could apply to any kind of image in order to estimate the gradients within an image. So why the gradients? Well, a good part of the fine scale details of my temperature fields are containing these like high variations within the field. So I wanted to include some kind of information about the gradients, the temperature gradients in my targeted fields to the loss function. So this would be the same temperature field from the 9 p.m. 13th of May 2019. And this is the estimated gradient thanks to the Sobel operator. And yeah, there's much information about the strong variations of temperature that could help with the smoothing that we observed earlier. So this is my new loss function. I have a classic MSE term that I conserved in my loss function, and then the penalization term containing the Sobel operator with a penalty weight that I tuned manually, so I did not do any model analysis on the value of it. I just tested several ones and observed which was the best trade-off between the penalty term and the performance of the model. And the second modification that I did to my statistical model was adding additional predictors. First, a seasonal predictor for the time of the day of the year, sorry. So implemented in the same form as the lead time of the model. And also a tone predictor in order to further introduce fine scale information into the learning of the model. So obviously I had to modify somehow my architecture, but it was done on the most straightforward of ways, like very simple and naive. So before adding my coarse like large-scale simulations in my network, I first did like the encoding for the town fraction. That would be my static predictor. Then once I reached the resolution of my inputs, I concatenated those and continued with the encoding. Once in the latent space, I injected also the day of the year with the time of the day, and then performed the decoding until the targeted resolution. Yeah. So, sorry, some results. Here in the figure, you can see, you can see the input degraded meson age, the targeted meson age at 300 meter resolution, and the downscaling results from these 4 different models. So I tried to introduce all my modifications in a controlled form, even though there's interactions between each modification that I did not quantify, because it's very, very difficult to quantify. So you have here a summary of what's inside the 4 models. For the simple model was the original one that I showed you earlier. So I have an MSE loss function and only 2 predictors, the large scale 2 meter temperature and the hour of the lead time of the model. Then I call Sobel when I add the Sobel penalty to my loss function, but have the same predictors. Season when I add the day of the year to my predictors, my set of predictors, and then the complete model with all my modifications. So already visually we could see like an improvement of the recovery of the fine details when the complexity of my statistical model increases. Gradients get sharper when we add the Sobel operator and then continue to improve with the rest of the additions. But maybe we need some scores to be sure. So on the top left, you have the RMSE for the different statistical downscaling models. So it's computed in a time series manner. So for each pixel, I will compute the RMSE between the targeted fields from my test sets and the predicted fields by the downscaling. So we can see already that for the simple model, there were errors made almost everywhere in a homogeneous manner all over the domain, but mainly focused on the two urban forests and some urban pixels. And then these errors get lower as we increase the complexity of the neural network, like as we introduce all the improvements in the network. And at the end, we're left with a quite homogeneous RMSE around the whole domain. On the top right, you see the mean error by month and lead time. So aggregated by month and lead time. On the left, the score for the simple model, on the right for the complete model. Concerning the simple model, we can see that we overestimate temperature in the winter and during the night, especially. So what that means is that when the minimal temperatures were achieved during winter, nighttime, our downscaling model doesn't reach those minimal temperatures. But during summer, when the peaks of temperature were reached during midday, so when we attain maximal temperatures, the downscaling didn't also reach. So we overestimate temperature during winter and underestimate temperature in summer. But once we include all the modification in the neural network, for the complete model, these biases are significantly reduced, even though we continue to underestimate somehow temperature during summer. And this is also the power spectral density for the targeted field in blue, the complete downscaling results in orange, and the simple model in green, and also the input. I added the input for some kind of reference. So degraded meson age at 5 kilometers for the same test case that I showed you earlier. So this is punctually for this day and hour. I maybe need to find better scores to evaluate performance over the whole test set, but it's a good way still to assess how well we recover the fine scale details. So we can see that we start to grow apart earlier for the simple model than for the complete model, but that we miss some fine scale details at the end of the, like for the finer scale. So as I mentioned before, I degraded my meson age inputs to 4 different resolutions, and I tried to downscale for all 4 resolutions to the 300 meter targeted resolution. So on the left, you have the RMSE by input resolution over the test sets, in blue for the simple model and in red for the complete model. We can see that it generally increases as the input resolution gets coarser, even though with the complete model, the RMSE stays quite lower than for the simple model. And again, some spectral information. We can see that, well, the best downscaling recovery was made with 1.2 kilometer inputs. That's normal, that's expected. But in general, all downscaling followed like the same trend. So I've talked about the perfect model setup. Maybe now I will show you what happens if we try to downscale real large-scale simulations. So this is the AROM output. This is the AROM simulation for the 4th of May 2019. So the same test case, but at midnight. And we try now to downscale this field to the corresponding meson age simulation. In the same way I did with my previous datasets, I selected the AROM forecast fields corresponding to the same data that I showed you earlier. But I needed to do some preliminary pre-processing of my fields because the resolution was not the same, and I wanted absolutely to apply the same network to do the downscaling in order to have better comparison between real large-scale data and the degraded one. One thing that I wanted to explore was to apply only inference to the AROM forecast. That didn't work, so I won't be showing this today. And then the other option was to reuse the same architecture to train a new emulator from AROM to the meso-NH resolution, and that's why I will show you now. Here you can see the AROM input for my downscaling model and the meso-NH input for the downscaling. Already we can see there's a big difference between the two inputs. So there's lots of physical information that differ between the two of them that we need to take into account. But we still have some urban information in the AROM inputs. In the middle, you have the output of the downscaling. So same architecture, same dates for training, validation, and test, only like different inputs. And then here, the targeted meso-NH fields. So we can see that actually the downscaling performed really well compared to what I expected it to do. For the urban heat island, it was quite well recovered actually, but we observed differences mainly in the countryside, but my opinion on this is that it's mainly due to the differences between the input fields, so there's not much that we can do to that for the moment. And for the spectral density, you have the two inputs here, then the target on blue, the downscaling of spectra from the degraded meso-NH in orange, and the downscaling from AROM inputs in green. We can see that actually the spectra is better for the degraded meso-NH, but that's normal. But then the recovered information is much more or less the same. So, discussion on future work. I've developed an emulator, a statistical descaling model in the perfect model setup to perform the downscaling. Now we know that downscaling is possible for 10, 5, 2.4, and 1.2 K resolution to the targeted hectometric 300 meters. I've submitted an article with everything that I presented today, well, with the perfect model part of my presentation, and I hope it will be up soon. On the AROM to meso-NH downscaling, is it good enough? That's a big question. For me, yes. With the differences between the physical, like large-scale physical information, for me, it's good enough. If we don't want to continue to tweak our networks, for me, it's the best we could achieve. Another perspective was maybe to do a two-step downscaling. So first learn the large-scale physical information and then perform the super resolution task with the model that I showed you today. Well, we need to think about if it's worth it or not. So I need to continue to evaluate my work. So if you have any scores in mind that I could use, I would be happy to take any advice. Also, but obviously the applications of this downscaling are very large and promising, we could imagine that we could have the downscaling plugged into the weather forecasting system and have very fine scale urban predictions. And also, we could do climatology studies now in urban setups with this kind of resolution. And for the rest of my thesis, what I'll be working on is the scaling over a bigger domain. So for now, I've focused on Paris because it's a very easy region to work with. There's no mountains, there's no sea, there's no sea breeze. Now I'm going to move to the Occitanie region. They are partially funding my PhD, so I need to show them something. It's obviously a much bigger domain. So the targeted through 300-meter resolution domain is much bigger. For my previous work, I've been working with a 16 by 16 matrix. Now I'll be working with a 1024 by 1034. So there's some questions about the viability of this project, if it's even possible to train with the resources that I have. So I selected another data set within the 2019-2025 period in order to represent at best the climatology in this in Occitanie. And yeah, so a bonus, maybe for a postdoc or something. Is it possible to build a generalizable downscaling urban model? That's a big question. I've started doing some bibliography on the matter. It seems very difficult, but maybe. So if you have any ideas regarding this, maybe come talk to me. I'll be very interested. And yeah, concerning the data, for the Maison-H Ile-de-France domain, these simulations are done. I've got them in the server. They're very heavy though, so if you want, we are happy to share, but maybe we need to be sure that the transfer is possible. And then for the Occitanie domain, the simulations have been started, but they are not finished yet, so I cannot provide it to you. But again, once they are finished, we'll be happy to share, if possible, depending on the weight. So thank you very much, and I will be asking any questions if you have.